I'm very thankful for the invitation to Mirko, Giovanni, Ludovico, Stefano. Thanks for organizing the workshop. I see it's also very well attended. So apologies to those who attended the workshop in Glasgow like a couple of weeks ago, because I'm going to give basically the same talk, right? So it may be a refresher or it may be, let's say, not welcome, but this is like, I didn't prepare a new talk after the Glasgow one. So I'm going to speak about fairness and transparency in rankings, about why do I think that algorithms can discriminate. I'm going to try to make some distinction about what we want to achieve with these fair algorithms or unbiased algorithms, something about measuring, and then speak a little bit about transparency. It's going to be all about rankings. And regrettable, I have another meeting immediately after this, so I won't be able to stay for the paper session. And it looked really interesting, the program for today. Unfortunately, I cannot join. So let me speak first about why do I think that algorithms can discriminate. I think this is an important topic because every time I think I mean, you have had this experience about writing a paper on algorithmic fairness, and you need to justify well what you mean by fair, what you mean by discriminating, right? And this is really key. So genetic discrimination, as defined by in this book Born Free and Equal by Kasper Lippe Rasmussen, is simply disadvantageous differential treatment, right? So there is an agent, which is X, that discriminates someone Y in relation to some other person, zeta, because one of them has a property and the other doesn't have that property, and because of that because of that property, X treats Y worse than what he or she will treat zeta. And it does it because Y has this property, right? So this is genetic discrimination, and we all engage in genetic discrimination. So for instance, in the selection of the papers for this workshop, the papers that, let's say, have a better technical contribution have discriminated from the other papers, so like in novelty, or that had a lesser novelty technical contribution or whatever, in an imperfect way, of course, but in some sense in a legitimate way. So there are legitimate ways of engaging in discrimination. Now, group discrimination is a type of discrimination where this property that is the reason why someone is treated worse than another. This property is a property of being a member of a socially salient group. And a socially salient group is, you're a member of a socially salient group when you have a characteristic that is very visible, that is very, well, salient, that is very obvious for other people, and that affects your relationships with others, particularly your relationships of power most often. So I mean, the idea of group discrimination is that the reason why someone is treated in a disadvantageous way is because they belong to a socially salient group, right? So this is like, and this is an instance of, let's say, group discrimination. Now, statistical discrimination is a type of group discrimination where this property is statistically relevant, or X believes that this property is statistically relevant. And this is different from non-statistical discrimination, which is another type of group discrimination, right? So for instance, if you suppose you have a person hiring a job interviewer, and this person decides not to hire a highly qualified woman because he believes that women have a higher probability of taking parental leave, then there is a statistical discrimination because the person is using a statistical belief to treat this person worse than another. Now, if instead the decision to not hire this highly qualified woman is because that person says, I intend to take parental leave, then this is non-statistical discrimination because it's not based on a statistical belief. It's based on a direct observation, right? And this, I think this is important because in statistical machine learning, which is at the core of, let's say, recommender algorithms, search algorithms, and so on, then if we disregard for a moment bad intentions or animosity, and we understand that these methods, by their very nature, they want to pick statistically relevant inferences from the data, right? So every feature that is part of a model after feature selection is because the model, the method because of this method, this feature has been considered as a statistically relevant, right? So then this is a statistical discrimination. So statistical machine learning systems can engage in a statistical discrimination if we disregard these intentions or animosity. Now, disregarding intentions or animosity is a big jump because it requires us to trust developers of a system, and it's very difficult to prove, for instance, that someone did not manipulate a training set to make the outcome worse for a certain group of people. And the fact that this is so difficult to prove, or the fact that we need to trust that this was not done, is a computer security issue. It's an issue of computer security. It's a gap that we are leaving open for bad things to happen, right? So there is another issue here, which is why we have these systems that require us to trust in that there is no bad intentions or animosity. That is not the case for many other systems, but for this one, we are asking the users to kind of blindly believe in us, and that's never a good idea, right? So let me speak briefly about algorithmic fairness in IR. So the objective of algorithmic fairness in IR is to provide the maximum relevance possible to the, I'm sorry, the purpose of ranking systems in information retrieval is normally to provide the maximum relevance to the persons who are searching, right? To the searcher. And this is why normally the results are ordered by the decreasing probability of being relevant. So the system that has the result that has a higher probability of being relevant is the result number one, and then the rest have supposedly a decreasing probability of being relevant. However, sometimes we do care about the items that are being searched, not only about the people who are searching. So for instance, if you're trying to find a local business, then and your items are business, then you are impacting the business success of these things. If you want to purchase a product, then you impact the marketing success. If you're recruiting a candidate, you impact the career success. And even in dating apps, you can impact the affective or even the reproductive success of people. So increasingly, the utility of the items, I mean, the items that are being searched are not just like objects, that they have interests, and it's important to honor those interests or to consider the utility for them in our calculation of what is the benefit that our system is bringing. Now, I claim that the system, that a ranking system, or perhaps even an information access system that is fair for those who are being searched, requires at least three properties. So first, there should be a sufficient presence of members of a protected group. Normally, these systems take as input people that are members of a protected group, and protected groups are not arbitrary; they are defined by law, particularly, for instance, by human rights law that states from the Declaration of Universal Declaration of Human Rights to the European Charter of Human Rights to national legislation embodying these human rights, including at the constitutional level. You have the idea that people should not be discriminated on must not be discriminated on the basis of, say, color, race, age, nationality, disability status, ethnicity, and so on, right? So this definition of what constitutes a protected group is something that is external to our system, is provided as an input. And we would like our information access system to have a sufficient presence of elements from this protected group. And this prevents economic harms or allocative harms, right? And distributional harms. So a second point is that fairness to for those who are being searched also involved having a consistent treatment of elements from both groups, protected and non-protected, and in general that similar items should be ranked similarly, right? And this prevents individual discrimination or inconsistencies. So third, there should be a proper representation of protected group. And by representation is something I'm going to unpack in a few slides, but it has to do with whether it reinforces stereotypes and the subordination of some minorities in front of others, right? So this is what I mean with a proper representation. Now, there are many other things that you can think as properties of a fair information access system or a fair search system, and from the consumer side, you would like an equal level of satisfaction across searcher group. And this is important because there is ambiguity that needs to be resolved, and that when you resolve this ambiguity, sometimes you favor one group over another, right? And this also prevents allocative harms in the sense that your system provides a good service to everyone, not only to a particular specific group of people. Right? So let's speak briefly about representational harms, because those are the harder to model, and those are the more difficult to model and computationally, right? I think we are very used to model allocative harms, but not so much representational harms. So representational harms happen when a system reinforces subordination of one group to another. This is the definition by Kate Crawford, and here there is an example from 2013 that there is an entire book about this topic, which was written by Safiya Noble, and it's called Algorithms of Oppression. And she describes her, let's say, how um, this observation that if you search something like black girls in a search engine, you will find very highly sexualized search results, which doesn't happen if you search for white girls. And at that point, it happened if for any group, right? So a query for Chilean men will show a variety of people who are from Chile, but a query for whatever Japanese women will show a very highly sexualized search results, which is representing women in an objectifying way. Also, search suggestions are another place where representational harms can happen, because the suggestions may reinforce stereotypes, may spread misinformation, may be manipulative, they may point to adult material, and so on, right? So for instance, these are some real examples, or some let's say a paraphrase examples from a paper on search completion by Alexander Oltanu and collaborators, where they also describe like how difficult it is to have a such a suggestion, and the many ways in which such suggestion can produce a representational harm. Now, I don't know if I should be attentive of the chat while I'm doing the talk, right?
No, don't worry.
Right.
We will have this. We will cover this in the question time.
All right, perfect, perfect. So, so as like the and I said in the beginning that we want a sufficient presence of people from the protected group, and this is a problematic statement on its own, right? So, what is a sufficient presence, and how do we define it in a ranking? So, for instance, take these three queries done against a recruiting search engine that is similar to LinkedIn, and you search for economist, and you find in the top 10 results that result number 1 is a woman, and results 2, 3, 4, 5, 6, 7, 8, and 9 and 10 are, I think I counted the number twice. Well, all the other results are men, right? So if you look at the top 10, there is a 90% of men. But if you go deeper down this list, you will find that the proportion of men is not really 90% among the economists listed on this website. But if you go to the top 40, you see 73%. And something, the opposite happened if you search for market analysis. And again, there is a bias towards men if you search for copywriter. And this shows something that I think it's quite prevalent, which is that when there is a difference between two groups, for instance, there is in this case 73-27% share. So when you look at the top 10 results, or you look at the top 3 recommendations, like the things that are really shown to the user and the things that really matter, they tend to exaggerate this gap that exists in the data. And that is not good. At the very least, we should try to avoid, let's say, exaggerating the differences there are. And maybe we want to reduce those differences, which is another topic I would like to talk about, which is about what do we mean when we want to reduce this bias. And here, I think something that we must accept is that as a research community, there are certain values that inspire our work. And I think perhaps everybody who came to this workshop today, or almost everybody who came to this workshop, has some egalitarian ideas, or egalitarian ideologies, or egalitarian ideals even. And so in recognizing that, we need to have enough introspection to be able to see what we're trying to achieve when we want to create this fair information access system, fair rankings, fair recommenders, fair search. And I think there are basically two goals that once we have established that the system is discriminatory in the sense that it produces a disadvantageous differential treatment against some people that have in common that they share a socially salient attribute. So when we uncover that that discrimination is happening, what do we do? And here there are two things that we can do, and they both are different. So one is the case situation where you have a protected group that has higher utility, but somehow is featured less, has a lower ranking in the search or in the recommendation, right? So for instance, an example of that is what happens with admission tests to the university. Uh, our observations and the observation from other groups have shown that there is a big group of students from marginalized or less privileged background, let's say students who come from public high schools, or their parents are middle low income, and so on. And this group tends to perform worse than their peers in standardized tests that are used to enter university in the countries that apply this standardized test. But the ones that enter university tend to have better grades than the students from more privileged background that obtain the same score in the standardized test. What I mean by that, like assuming that that is the case in some situations, what you have is a standardized test that is discriminatory in a very narrow sense, in the sense that is providing you, is giving you lower rankings for people that give you higher utility. From the perspective of the university, you don't want people with high standardized test score. That is just a proxy. What you want are people who will get good grades in the university and will graduate and have a very high probability of graduating, even when subject to a very demanding program. This is what you want. You're using the standardized test as a proxy. And by using a system that gives lower scores to underprivileged students that will perform better than others in the university, both the students of those groups and the university are being harmed. So in this case, the goal is to reduce discrimination. You want to make sure that this group that has higher utility has higher ranking. And that is a very uncontroversial thing to do. However, this is sometimes this is not what you want to do. Sometimes you realize that the group that you want to promote has both lower utility and lower rankings. So you may have, again in the case of university admission, perhaps there is a particular group like students from very low income backgrounds, or from regions that are far apart from cities, like rural communities, low income backgrounds, parents without much education, and so on, that will struggle both in the standardized test and in the university. Maybe even their chances of graduating are lower than the ones of their peers. But given the objectives of the university in society, or a voluntary commitment, or whatever, there is some reason that makes a university adopt a policy by which they still want to admit these students. Or maybe in the case of a search engine, you realize that your users do not like certain items that are produced by a group that is marginalized. Well, perhaps you still want to promote those items, but at that point, what you're trying to do is not to reduce discrimination. Or you can say in this framework, what you want to do is not to reduce discrimination. What you want to do is to provide equal opportunity. And these are two different goals. Maybe you use the same technical tools, but we must not confuse one for the other, right? And one has to be honest about what you want to achieve, right? So do you want to make everybody better off, or you want to make sure that the groups are placed in an equal footing in your search engine? And perhaps for some groups, you see a very clear case of discrimination and you can fix it, and it's very fix it. I mean, re-rank the items, or create a different ranker or a different recommender so that it doesn't happen and everybody's better off. Or you may want to make sure that this group is better off, or is not as historically disadvantaged as before. And that is about providing equal opportunity. Now, when you find these biases that harm the searcher utility and you want to reduce discrimination, this is relatively easy to implement in a company. However, then there are things that are harder to implement. If you have legal mandates and voluntary commitment to provide equal opportunity, then that needs a broader agreement within a corporation, a university, or an institution. If you want that to be sure that technology embodies certain values, then you have even a more difficult proposition, and you need to get the agreement of more people to the table so that that can happen, right? So it's not always easy to make a case of creating fair ranking. Perhaps it's important to know what you want to achieve. So then another um, issue that we have to discuss is where do these biases come from, right? And I think there are at least three places, and two of them are quite obvious for you, for this audience. You may have biases in the training data, and of course, both expert-provided training data and user-provided training data. You may have racist users, right, that click on some results and not others, sexist users, and so on. So you have a bit of an adversarial relationship with your users, and you need to verify what are the training, what are the characteristics of the training data that the users are providing, because they may be biased, and this may spiral down. And it's not always a bias that harms another group. Sometimes it's a kind of self-harming bias, right? So if for any reason, and I mean really for any reason, you have an advertising ecosystem and you find that women don't click on ads for jobs that have a high pay, and you start to consume those clicks as if those were, let's say, true signals of relevance, then you may end up in a system where ads for high-paying jobs are never shown to women, and that's not what you want to achieve. Most likely, it's not what you want to achieve. So user-provided training data must also be taken with care, and there are tools for doing that. And there is a more subtle type of bias, which is in the document construction, because not everybody, for instance, in the case of a CV, not everybody fills in a CV in the same manner. Not all the recommendation letters are equal to one another. So if your objects have some properties that depend on gender or ethnic background or nationality, then a ranker that is trained on majority type of object will not rank well objects that belong to the minority type. So for instance, in the case of CVs, there is some research showing that women, perhaps, most likely they feel, there is a large group of women who complete very well their skills section in LinkedIn, but they don't complete as much the previous experience section, while there is a large group of men that complete very much the experience section, but not so much the skills section. So depending on the weight that you give to these different elements, your ranker may have a bias, and that bias doesn't come from the training data. It doesn't come from the training labels. It comes from the construction of the documents or the objects that you're ranking themselves. So let's talk briefly about some how to measure fairness in ranking, right? And I think I have here surveyed three possible ways of measuring fairness in ranking. One is rank weighted exposure, which is perhaps the easier to understand. Then there are probability-based methods, and there are pairwise methods, and most likely it's quite likely that there are many other methods. Interestingly, this rank-weighted exposure concept advanced in 2018 can be contrasted very clearly with a concept of retrievability that was advanced 10 years earlier and sort of rediscovered here in the rank-weighted exposure. And here at Sopardi and collaborators, they say, well, we need to be aware that different items are differently retrieved from a system. So ideally, we should be able to at least measure to what extent our corpus, different elements in our corpus are being surfaced by queries. And this is exactly an issue of exposure, right? It matches very closely to an issue of exposure. So the first metric of let's talk about rank weighted exposure as a measure of fairness. As all of you are well aware of, there is different positions in a search engine results page have different visibility, different probabilities of being examined. Sometimes this depends directly on the Sometimes in some models, it depends only on the position. In other models, it depends on the position and on the relevance of the items being placed there, right? So there are different types of, there are different ways in which you can define this loss, but in general, it's a decreasing function, this visibility of a position or this exposure of the position. And in a fair ranking, what you would like is that on expectation, the visibility given to certain groups is similar to the visibility given to other groups, right? In other cases, you want something a bit, this is utility agnostic, right? Here, we're not saying perhaps elements from one group are more interesting than elements from the other group, right? So this is a utility agnostic disparate exposure measure, but let's talk about one that is utility aware, right? So suppose you are hiring candidates for a job, and this job has some a very objective measure of metric of success. Suppose you want people for typing documents, and you have these typing speeds. So you do a typing speed test, and you get these scores about the typing speed. And it so happens in this example that 3 people have higher speeds at typing than the other 3, slightly more. Let's assume that that thing is the relevance of the items for the purposes of this example. Now, what's happening in this example is that the relevance, there is a very small relevance gap between one group and the other, but there is a huge exposure gap between one group and the other because exposure decreases very quickly. So what we are seeing here is a situation where the exposure and the relevance are not match, and you have a small gap in relevance that is turned into a big gap in exposure. Ideally, what you would like instead is to have like an utility normalized exposure. I don't know if my pointer can be seen. But in the top right corner, you have utility normalized exposure, which is that the exposure of the group divided by the utility of that group should be constant across groups. And this is a very popular measure of disparate exposure for rankings. Now, the same measure, maybe you cannot satisfy it in every query, and instead you want to satisfy it in an amortized manner. So you want a system that after, let's say, a day of queries, you have actually given the same exposure, an exposure proportional to the utility to all the groups, but you don't do it for every query. Instead, you do it in an amortized manner across several queries. And there are many other variants of this thing. So another way in which you may want to measure fairness in rankings is through a process of randomized merging and a probability-based scheme. And this all starts with this 2017 paper by Young and Stojanovic, where they say they propose an ideal process in which you rank items separately. You rank all the men on one side, you rank all the women in the other side, for instance, in this case. And now you do a randomized merging in which you toss a coin with probability P, you pick an element from the protected group. With probability 1 minus P, you pick an element from the non-protected group. And these are 3 realizations, possible realizations of this process with different probabilities, right? With probability 0, you always pick men until you don't have any more men, and then you start picking women in the list. With probability 0.5, in a, let's say, in a cartoonish way, you will pick 1 man, 1 woman, 1 man, 1 woman. Obviously, that will not happen exactly because it's a probabilistic process. So this is the randomized merging process that they provide, and this can be turned into a representation, into a fair representation condition for groups, because now, given certain parameters like the probability, significance parameter, and the size of the list, you may do a statistical test and say, well, you claim that your probability of selecting a woman was 50%, and in your list of 10 elements, you have four women. Is this consistent with the proposed process? And you say, well, depends on the significance of your test, but in some cases it will, right? So for instance, with significance 0.1, using a binomial test, you have to have among the top you need to have at least 3 elements, 3 women in the top 10 positions for this to satisfy the binomial test at a significance level of 0.1, right? So um, you can have certain tolerance, which is given in this case by this parameter alpha. Now, this applies to the entire top 10 list, and you can have a ranked measure using the same, where basically what you will do is that instead of having a fixed k, is that you will apply this test for every position, right, from 1 to k. And so that means that no matter where a user stops examining the list, the user has seen a sufficient number of members of the protected group, where sufficient is given by the binomial test with the significance that we are using. Now, this is requires some adjustment because there are multiple hypothesis testing, but this can be, it's not trivial to fix, but this can be done. So you need to adjust the significance of each individual test so that all the tests together have the significance that you want. And these are not independent tests because the prefixes overlap, right? So, but in the end, you get a measure. You can get a measure of this list. What probability does it represent? Or if this list came from a randomized merging process, what is the largest probability of picking up members from the protected group that I will accept as valid, given the observation of the list that I'm being shown. And this can be used to compare lists of different lengths, for instance. And this slide comes from a master thesis of a student that what she did was to look at different job search platforms in the Spain, France, and the UK, right? She looked at LinkedIn and Viadeo, which is another job search platform, and she looked for the same profession in the different search engines. And she found, of course, that there are many different large differences in representation of women, in the presence of women, across professions, across countries, but even across platforms, right? So you may have in the same country two platforms, one of them having 10% of women in a profession, the other one having 30%, or one of them having 30. For instance, in the case of Spain, LinkedIn was showing a proportion of women that would mean that economists make about women economists are about 30% of economists, while in Viadeo you will have that women economists are about 60% of the economists, right? And so you choose your platform and you have a different proportion. Now, moreover, and something more problematic, and many of the participants in today's workshop come from a country where the native language has gender names in professions. Like, for instance, in the case of Spanish, you have científico and científica, or profesor and profesora, like men and women. And what we've also found out here was that these things were inconsistent across the expansion of gendered profession names was inconsistent across search engines and even within a search engine, which means that for some professions, let's suppose designer, it was enough to query for the profession name in masculine to get both men and women. But in other professions in the same search engine, you will need to say a male designer or a female designer, diseñador or diseñadora, or escritor, escritora, to be able to find both men and women, right? So the expansion was inconsistent. So a third family of measures of fairness look at pairwise comparisons, right? And these are very interesting, and I think they are very intuitive. So as you may, you're probably aware of, like the area under the curve measure for classification, for instance, measures what is it's equivalent to measure what is the probability that you have a relevant item ranked above an irrelevant item. In other words, if you pick one element and another that one has a high score and the other has a low score, what is the probability that that happens? What is the probability, for instance, that one is relevant, that okay, if you pick two elements, one relevant and one irrelevant, that's if you pick two elements, one relevant and one irrelevant, what is the probability that your ranker has positioned the relevant item above the irrelevant one? So that is equivalent to AUC. And you can define with that a kind of cross AUC where both elements belong to different groups. So in this case, of course, you want the probability that relevant item from one group is ranked above an irrelevant item from another group to be high. But you also want the opposite to be true. You want this to happen irrespectively of which groups, of whether you swap the groups. You just want relevant items ranked above irrelevant items, even in a cross group manner. And the difference, the gap that may exist when you do this in one ordering and you do it in the opposite ordering is what they call the delta cross AUC in this paper, and it's a measure of unfairness. Ideally, you want this to be as close as zero as possible. And there are ways of operationalizing the same idea, that you pick an element from one group, an element from another group. One is relevant, the other is irrelevant, and you want to make sure that they are ranking in the correct position irrespectively of which groups you pick. So I'm going to skip the part on fair rankings, so to creating these rankings, which is basically different variants. The only part I'm going to show you that perhaps makes a lot of sense is to know that there are three places where you can do this intervention, and this is well known in the algorithmic fairness literature from the data mining community, which is that when you detect these issues and you decide whether what you want to do is to reduce discrimination or you want to provide equality of opportunity, then there are 3 points of intervention. One is changing the training data. And the most obvious intervention there is, for instance, making sure that the training data passes a test of unbiased, right? Or passes the same test that you will apply to the output. The second intervention is that you can change the algorithm itself. And in the case of learning to rank, in the case of recommender system, this is usually done by applying a penalization. You add a penalization term that penalizes unfairness, and you just have to define that penalization term in a way that allows you to do efficient optimization. And the easiest way of applying, let's say, a mitigation measure to unfairness is to do post-processing. And normally the first algorithms that are proposed it happens in data mining, machine learning, and AI. The first algorithms that are proposed are post-processing methods. They look at the output and they re-rank, filter, or move the items in some way so that the system satisfied in either query by query or in an amortized manner some criterion of fairness, right? These are the 3 intervention points. The more difficult one to do is in-processing methods, because those require you to understand very well your algorithm and modify it. The easiest one to apply are post-processing methods and so on. So let me speak briefly about transparency, because I think it's a very important topic. So transparency is important because it allows us to support ethic compliance, to test our system, to make the trade-offs visible, and so on. Now, transparency and explainability methods need to have a very clear audience, right? So not all the transparency methods, it's very difficult to have a transparency method that is good enough for everyone. Normally, you need at the very least one transparency and explainability method for end users, and some transparency and explainability methods for the developers, and most likely some transparency and explainability methods for potential auditors that want to look at how your system works. Explanation should be good enough, particular explanations for users, for end users, should be good enough that they allow the users to challenge the ranking, to say, well, your machine should have placed my business above the other because of this reason, right? So an explanation should empower users, not only users. Of course, users should be able to understand the explanation, but we want more than that. We want users to be able to challenge your system. Now, I think explanations are important, and I have said this a number of times, are important because there are people like this guy who do this, make these claims. Like, for instance, he wrote in 2018, in August 2018, well, if I search for Trump news, I only see news from CNN and I don't see news from conservative media. Does it mean, this means that Google and the others are suppressing the voices of the conservative and hiding information and news that are good? So I think this is a very problematic claim because it cannot be falsified. So how do we prove that he's wrong? Like the only thing we can do is to trust Google's engineers when they tell us that they don't have this issue. But again, that's a computer security problem. So I think transparency here is just broken because there is no way we can certify that that's false, right? And this is very problematic because then why should we trust Google for news? And this is part of an increasing trend towards secrecy, and that is maintained in a variety of ways. I think one of the main messages of Fran Pasquale's book is that secrecy is maintained by legal, technical, social barriers, and they pile on top of each other. So you have to cross through layers and layers of problems to be able to see what an algorithm is doing. And Zeynep Tufek, she claims, well, this is transparency in news is really problematic because if you go to a demonstration and then you turn on your TV in the evening and you don't see news about this demonstration, you can claim that the TV is suppressing information. But if you don't see it in your Facebook feed, then what does it mean? Does it mean that it didn't happen, or is it not being shown to you, or it's not being shown to anyone? Right. So what is the how can we know whether they are suppressing the information or not, and except trusting them, right? So computational information, algorithmic information is very difficult is very technically complex, but I think there are good reasons to believe that this can be communicated to the public. And here, I think and the final idea I wanted to talk today is about nutritional labels, right? So nutritional labels are technical information in food. Like, and I can imagine like this discussion about nutritional labels saying, okay, people don't know how much what people don't know what is magnesium, what are the sources of magnesium, or how much they need in a given day. Like, why should we provide this information to them? And in truth is, maybe we still don't know. Let's say I don't know what magnesium is for in my diet, but I can, through the nutritional label, I can understand, for instance, if this has food has too much or too little of it, what is the daily recommended intake, and so on. So over time, with using a consistent mechanism for explaining things, like more like a normalized way of explaining things, people can learn about algorithms. And in this case, there is this nutritional label for ranking proposal. They say, okay, what are the ingredients of this ranking, which means what are the features, whether this ranking passes the fairness test in different ways of having the fairness test, and so on, right? So this is interesting information that allows the consumer to see if the information he or she is consuming is a balanced information diet, right? So transparency can help us because it can help us. As I said, many of us have an egalitarian ideologies, ideals. Um, Transparency can help us to avoid sneaking affirmative action, or, as I said, like equality of opportunity when this is not welcome or without a consensus. And it also allows us to avoid certifying an algorithm that is part of an unfair system. So in conclusion, I would say that IR and recommender systems are catching up increasingly with machine learning and data mining, where issues of fairness have been studied more. Sometimes algorithmic fairness requires solving an algorithmic puzzles. Other times it doesn't. It's important to know what is the problem that you're trying to solve, either in a recommender system or in a ranker, like whether you're trying to equalize opportunity or reduce discrimination. And different solutions address different problems, right? So, okay, I want to do a shout out to Meike Selike. She's a PhD student of mine with Yang and Stojanovic. They released very recently, I would say less than a week ago, a survey on fairness in ranking. There is an excellent tutorial on fair information access by Michael Ekstrand and Fernando Diaz and Burke. They have given this tutorial in many places. And of course, you're welcome to look at the proceedings of the FACT conference, which also contain, let's say, many papers that you may be interested on. That's it.